Welcome to this heat transfer video. We're going to continue talking about natural convection, which is also known as free convection. And specifically, we're going to be talking about free convection correlations. So just like with external and internal convection, there will be a procedure that we go through to calculate the Nusselt number, which is the dimensionless heat transfer coefficient, and we'll use that to back solve for H, which is our convection heat transfer coefficient. So let's first go through some definitions. There are going to be some new dimensionless numbers that we'll need to cover in free or natural convection. So first of all, we want to introduce the thermal expansion coefficient, beta. So beta is a measure of how much a fluid's density is going to change with respect to its temperature. So if the fluid expands quite a bit with temperature, like air, then it's going to have a relatively high magnitude beta. For an ideal gas, this ends up being equal to 1 over the temperature. But you can imagine something like water, which is an incompressible fluid, doesn't expand nearly as much, so it's going to have a smaller beta. So you'd actually expect to get, relatively speaking, better free convection with something that has a higher beta, and that'll be measured by some dimensionless numbers that we'll talk about soon. So one of these dimensionless numbers is called the Grashof number. So the Grashof number is analogous to the Reynolds number. So when we talked about forced convection, we talked about the Reynolds number. When we talk about free convection, one of the numbers we'll deal with will be the Grashof number. There will be another one that's also analogous to Reynolds number, which will be the Rayleigh number. So the Grashof number is analogous to the Reynolds number in that many of our correlations for Nusselt number, rather than being a function of Reynolds number and Prandtl number, for free convection they will be a function of the Grashof number and the Prandtl number. So the Grashof number is defined as follows. It is G, the gravitational constant, which you should be familiar with, is 9.81 meters per second squared. Beta, which is the thermal expansion coefficient. Then we're going to actually measure the temperature change in going from our surface temperature to the bulk fluid temperature. Our dimension shows up in there as L cubed, and that is all divided by the kinematic viscosity squared. So this is a number that we'll be dealing with as you go through convection correlations. When you do have mixed convections, when you have a combination of free and forced convection, you may see some correlations that where the Nusselt number is a function of Reynolds number, because if there is forced convection in there, remember that Reynolds number helps us to characterize that forced flow really well. And then when there is free convection in there, then the Grashof number will do something similar. And then in both cases, whether it's free or forced, we would use the Prandtl number. So you may find correlations where researchers have studied the effects of both free and forced correlation combined, and they might put their results into a correlation of this form. So let's go ahead and look at some of these correlations. So correlations for free convection. So when you have laminar flow on a vertical isothermal plate, so here is our plate, it has uniform temperature T sub S, and that convection is happening from the plate out to this bulk fluid at T infinity. So the boundary layer is going to form like this if it's a heating example, and so we would get this local Nusselt number. So again, because we have this formation of a boundary layer, you can imagine the Nusselt number and H, your convective heat transfer coefficient, changing. And typically you would see a higher, if it's all laminar flow, you would see a higher Nusselt number. Sorry, not a higher Nusselt number here. You would see a higher H here because the boundary layer is thinner. As the boundary layer gets thicker, there is more thermal resistance, and so you typically see a lower H here. And again, this is all for the laminar case. If you recall, when the flow starts transitioning to turbulent, you get a lot more circulation, and that circulation creates more advection, so your convective heat transfer coefficient will increase when you have turbulent flow. But we are talking about laminar flow for these particular correlations. So the Nusselt number correlation is going to be equal to the Grashof number, which is also a function of x. So x being measured in this heated plate example from the bottom to the top. If it were a cooled plate example, x would be measured from the top to the bottom, and because our fluid flow would be going the other way. So for a cooling example, our boundary layer would form from top to bottom, and you'd measure x from top to bottom. So this g parameter is something that is important to point out. This is not the gravitational constant in this particular correlation, and it's an unfortunate choice of nomenclature by our textbook, in my opinion. So g just refers to a function, and this function is a function of the Prandtl number. So basically, you would evaluate the Prandtl number for the fluid in this particular circumstance, and you would plug that Prandtl number into this equation. As you can see, this is just an empirical equation. It doesn't really have much physical meaning, and there's not a ton of use in trying to put direct physical meaning behind this, but that gives us g as a function of PR. And then we would plug in this g as a function of Prandtl number into our Nusselt number correlation. So again, keep in mind, this is giving us a local Nusselt number, which is going to yield a local convective heat transfer coefficient. So we would, in using this correlation, we would need to use a local Grashof number because we are getting a local Nusselt number and a local heat transfer coefficient. So as we noted before, if it's a heating application, we would measure x from the bottom of the plate going up, and if it is a cooling application, we would measure the x from the top of the plate going down. Here again is the definition of the Grashof number, so we'd calculate that as a function of x and plug it into the correlation above. If we wanted to get the average Nusselt number, we would instead evaluate these dimensionless numbers as a function of L, where L would be the total plate length. So here's 0 and here's L. So to get the average Nusselt number, you'd basically do this integration of the local Nusselt number, or do the integration of h from the entire length of the plate from x to L. And doing that integration yields a correlation of this form. So now our Grashof number is a function of L, and our local heat transfer coefficient is an average local heat transfer coefficient. Our Nusselt number would be a function of this L. So when we're back solving for h, we would just substitute in x equals L. So this is the laminar flow example, and certainly, as I mentioned before, flow can become turbulent. So that flow becoming turbulent would be measured by a new dimensionless number. This is called the Rayleigh number. So typically the Rayleigh number is also kind of analogous to the Reynolds number for forced convection. The Rayleigh number, though, would be the Grashof number multiplied by the Prandtl number. So those are both dimensionless numbers, meaning that our Rayleigh number is also a dimensionless number. And typically, so as we spell out the Rayleigh number, it takes on that form: g, the gravitational constant, beta, the thermal expansion coefficient, our delta T from the solid surface out to the bulk fluid, x to the third, and then we would have our alpha, which is the thermal diffusivity, and our kinematic viscosity here. So typically you would start to see transition from laminar to turbulent at a Rayleigh number of about 10 to the 9th. So this is what this means, the subscript x comma c. That is the C stands for the critical Rayleigh number, and Rayleigh number is measured by x. So you would get to a critical x, so x would be the point measured in space or in distance from the leading edge of this plate. X sub c would be the point at which the flow transitions from laminar to turbulent. So the correlations for laminar versus turbulent flow actually sort of get glommed together. I think it's just more difficult to determine when that flow actually transitions from laminar to turbulent, and researchers who study these kinds of things end up having correlations that are kind of equally applicable in either case. So whether you have turbulent or laminar flow on a vertical plate, for any Rayleigh number, whether that's laminar or turbulent, you could calculate an approximation of the Nusselt number using an equation like this. So this does get a little bit ugly, but you can see the basics are there. It's a function of the Rayleigh number and the Prandtl number, and that's it. And the Rayleigh number would be evaluated at the plate length. So this correlation would be a good approximation of the Nusselt number, the average Nusselt number over the entire length of the plate, whether that flow is laminar or turbulent. If you knew for sure that the flow was laminar and you wanted to use an equation that were a little bit more accurate, you could use one of this form. So for purely laminar, this may be a better form of the equation to use. And note that this is only when the Rayleigh number is less than the critical Rayleigh number, ensuring that your flow would be laminar. So note that these are average relationships in both cases because of that bar, and notice that because of the subscript L, the L would be your critical dimension that you're using as you're calculating the Nusselt number, and then as you're back solving for the average convective heat transfer coefficient. So we would evaluate both of those numbers using L as our critical dimension. There can also be situations where you have horizontal heated plates, certainly. So these get a little bit different whether the fluid is, depending on which direction the fluid is going. So if you have a let's see. So the physics get a little bit more complicated when you have horizontal plates. So here in the top, we have cooling examples. When the plate is when the plate is cooler than the surrounding air, so that because the plate is cooler, that's going to create a downward fluid flow. So depending on if it's the top part of the plate or the bottom part of the plate that's exposed, you'll actually get a different correlation. And you can see why physically. So if the bottom part of the plate is insulated and the top part of the plate has this cold surface exposed to the ambient fluid around it, you'll see that the plate is going to create this downward draft. So that flow is going to have to go out to the edges of the plate and then down. Whereas if it's the bottom part of the plate that's exposed, you won't have this overall downward flow coming from above the plate and then going below. It'll all be below the plate, and so you'd get more kind of circulation, a little bit of turbulent effects there, as that fluid's going to have to find paths downward. So similarly, when the fluid is heated so in heating applications on the bottom, when the bottom part of the plate is exposed, that flow is going to have to go around. So this situation is kind of analogous to this situation. If the top half of the plate is exposed, then you get this extra circulation here as that fluid tries to find good paths to. So there will be a little bit of turbulence and tortuosity as that fluid has to be heated and then find its way up. So this situation is analogous to this situation. So the correlations look like this. So you have to be just careful as to how you're applying these correlations. So if you have the upper surface of a hot plate or the lower surface of the cold plate, so that would be this situation or this situation, you could apply correlations of this form, that the Nusselt number is equal to 0.54 times the Rayleigh number to the 1/4 power. This would be applicable when your Prandtl number is greater than 0.7 and your Rayleigh number is between 10 to the 4th and 10 to the 7th. For higher Rayleigh numbers, when the flow goes through that transition regime from laminar to turbulent, then you would get a correlation of this form, and this would apply for all Prandtl numbers. So again, these are just empirical correlations generally. I would encourage you to just get to be more comfortable with the process of how to find Nusselt number and then convective heat transfer coefficient, and don't get too bogged down by all the little nitty-gritty details that go into these correlations. So if you do have the lower surface of a hot plate or the upper surface of a cold plate, so that is of course this situation, then you would have the correlation Nusselt number is equal to 0.52 times the Rayleigh number to the 1/5 power. This particular correlation would be applicable from Rayleigh numbers of 10 to the 4th up to 10 to the 9th. As you go through the book, I'd encourage you to skim through your textbook because there are some correlations that I'm not covering. I'm really trying to emphasize this basic idea of what dimensionless numbers do you have to calculate and how to go about finding the right correlation. Once you've found the right correlation, it's really a matter of plugging and chugging and doing some of that nitty-gritty detailed calculation work. Another very relevant situation is a horizontal cylinder. So think about instances where you might find a horizontal cylinder. Basically, any pipe or duct would be a horizontal cylinder. So if that duct is at a temperature that is different from the surrounding air, you're definitely going to induce free convection. In this particular example, the pipe is hotter than the surrounding air, and this looks a lot like the example I showed as we introduced this topic. So you can see that this heated pipe heats up the fluid immediately around it, and you get this plume of airflow going from the pipe upward. So notice we won't really deal with local heat transfer coefficients or local Nusselt numbers when we're talking about free convection for flow around a horizontal cylinder, but notice that the Nusselt number may actually change as you're going angularly. So notice this angle theta. So if you notice here at the bottom, because we have this thinner boundary layer here, so because of that thinner boundary layer, when theta equals 0, we tend to get higher Nusselt numbers. There's less thermal resistance going from pipe surface out, and you're going to tend to get some good fluid velocity going this way. But as you go around, you'll start to see that your Nusselt number, as measured by theta, or this angle around the pipe, would start to tail off. To here we have the lowest Nusselt number, so heat transfer is going to be the worst here because it has this much thicker boundary layer that heat needs to propagate through. Again, we really won't deal with this much in this class. We'll typically just be calculating the average Nusselt number. So when we're talking about averages, we'll just average out what's happening all along here. So in dealing with that average, we will calculate the Nusselt number. Our critical dimension will be d, or this outer pipe diameter. And that's what's going to show up as we back solve for our average convective heat transfer coefficient. So here's the correlation in this particular case. So the Nusselt number is a function of the Rayleigh number and the Prandtl number, and there's lots of funky powers in there. This particular correlation would be applicable for Rayleigh numbers less than 10 to the 12th. And again, where this kind of limit comes from would be some person in a lab doing some experiments, and they would find that their correlation fits best only in this particular range. So just as you scour through different heat transfer correlations, just make sure that your particular situation meets the specifications required by that correlation. So there are, as you go through the book, you'll see a whole bunch of different heat transfer correlations in there. So it's really just a matter of identifying your geometry and then trying to find the right correlation that matches your geometry and flow conditions. So what happens when we have mixed convection? So again, mixed convection is a combination of forced and free convection. So a good metric for determining if you need to care about one or the other, you could take this ratio of the Grashof number and the square of the Reynolds number. So if the Grashof number divided by the Reynolds number squared is much, much less than 1, then that means we have a very small Grashof number compared to the Reynolds number. So that very small Grashof number means that free convection or natural convection is not going to be an issue. It's going to be something that we can neglect. So we would typically just use a correlation for a forced convection kind of a situation. So that would take on the form, the Nusselt number is a function of the Reynolds number and the Prandtl number, and we really wouldn't need to worry about free convection at all. If the opposite is true, and this ratio, Grashof number over Reynolds number squared, is much greater than 1, that means that free convection tends to dominate. Our Grashof number is large and our Reynolds number is small, so in that case we would ignore forced convection and just focus on free convection. And those correlations, as you just saw, are going to be a function of the Grashof number and the Prandtl number. And you notice that the Rayleigh number also showed up in some of those correlations, but the Rayleigh number is just Grashof number multiplied by Prandtl number, so this relationship holds true. Okay, so if we determine that free convection and forced convection are kind of on the same order of magnitude, so if the ratio of our Grashof number to the Reynolds number squared is approximately 1, then we would need to include both the effects of forced convection and free convection. So then we would find Nusselt number correlations that are a function of Reynolds number, Grashof number, and Prandtl number. So we would need to include both of those effects. Most of the free convection correlations that you find in our textbook are of this form. So another way of dealing with mixed convection is using this rule of thumb. So the Nusselt number, this is to the nth power. N is typically 3. Again, this is a rough rule of thumb to give you an approximation for the Nusselt number under these mixed conditions. So the Nusselt number to the nth power for mixed would be equal to the Nusselt number to the nth power for forced plus or minus the Nusselt number to the nth power for natural or free convection. So the way you would do this is you would calculate the Reynolds number and subsequently you'd calculate the Nusselt number for forced convection. For natural convection, you would calculate the Grashof number and potentially the Rayleigh number, and you would calculate the Nusselt number. Then you would raise each of those to the third power and use that to calculate the Nusselt number to the nth power. So to just get the overall combined Nusselt number, that would be Nusselt number for forced convection plus or minus Nusselt number for natural convection, each of those to the nth power, and then you would just take that quantity to the 1 over n. So one thing, you may be very confused right now because we have this plus or minus in there. So what does that mean? Which one do you pick? So that is shown here. So you would use a plus when forced and buoyancy flows are in the same direction or in the transverse direction. So basically, when forced convection and free convection are working together, these quantities are additive. When they are working against each other in terms of flow, when the flows are going against each other, you would use a minus sign. So let's just give a quick example of that. And I'll maybe pause here and have you think about it. So let's say we have a heated pipe. And let's say we have flow. Let's say maybe this is from the building's circulation system. Maybe this is just below a vent. And we have our flow going downward. So in this case, we have Ts. Here is T infinity. Because the pipe is heated, Ts is greater than T infinity. And then we have, this colder flow coming down. So stop and think, would you use the plus or the minus in this equation? Are those flows working together or against each other? So in this particular case, the flows are working against each other. That heated pipe is going to create a buoyancy flow going upward. So those flows are going to be going against each other, and their effect would be based on this difference. You'd use the minus sign in this case. So instead, if this were a cooled pipe, or let's just say a cool pipe, and we have this downward flow from the building's ventilation system, well, this cool pipe is going to generate buoyancy flow going downward. So in that case, the forced convection and the free convection are going in the same direction, and we would use the plus relationship there. So that's how that works. And then if you have traverse flow, so let's say instead that flow is coming from the side, and that is at t infinity. So we are still going to have that fluid come in and sweep away this boundary layer. So in that particular case, because it's traverse flow, we would use the plus condition there too. And this is a kind of a rough rule of thumb, and because these situations obviously get quite complicated when you have convection is quite complicated already, but then when you have combined forced and free convection, you can imagine things getting even more complicated. So the relationships that we're dealing with, consider them always to be approximations. But for doing design work or evaluation work, these are sort of all you've got unless you're running actual experiments on your system. So to summarize, convection is really complicated. A lot of it boils down to this simple procedure that we've talked about before. So I really want to emphasize, I don't think it's very valuable to try and memorize equations. Certainly don't try and memorize any of these complex convection correlations. And maybe you don't even really need to remember the names of the equations and even the geometry. Really, this is something where you'd have to be resourceful. You'd have to recognize what your geometry is. So first, evaluate your geometry. The same procedure that we covered in external convection and internal convection is certainly applicable here in forced or free convection. I mean, in free or natural convection. So you still, for example, you may have flow over a flat plate. You need to look at if that flat plate is horizontal or vertical. Remember, we saw different correlations for those different situations. That flow could be around a cylinder. There's flows through, free convection flows through channels, and those, or flows across a plate at an angle, or flow around a sphere. There really are a whole bunch of these. So it's helpful to learn to be resourceful, and just really what I hope sticks with you is this process. When you need to characterize a convection process, know that finding the convection correlation is, or finding H is not trivial. You have to go through this process of finding H. So after we evaluate the geometry, we would evaluate our fluid and flow conditions. So those are certainly, if it's forced convection, those are a function of the Reynolds number, and the flow could be laminar or turbulent. And then for free convection, we introduced some new numbers, the Grashof number and the Rayleigh number. So those would certainly need to go into our calculations as well. And as always, the Prandtl number is a really critical number here. So we'd still try to find the appropriate temperature to evaluate the different fluid properties, such as viscosity, thermal conductivity, and the Prandtl number itself. So then we would use the appropriate correlation. Again, that could be local or average. I showed some local correlations and some average correlations, and sometimes the local correlation is not available, but almost always the average correlation is available, and that's because the average you can obtain by integrating the local. Finally, you back solve to find your H, where that comes out of the definition of the Nusselt number. The Nusselt number is a dimensionless heat transfer coefficient. So, and that definition is the Nusselt number is equal to HL over K, where K is the thermal conductivity of the fluid. And again, this can be local or average. So again, I just want to emphasize this procedure is what I hope will stick with you long term. And you'll have web references or literature references or a textbook or a database to go and find the different fluid properties and all the different correlations that are available.